So we've now got a triple sum down here. But that last summation is exactly what you need for the finite form of the Jacobi triple product identity. And so we wind up with this particular identity. And what's nice about this is that each step can be proven purely combinatorially by bijective proofs. There's a simple bijective proof that these two sides are equal to each other. And if you let x be minus 1, you get the first of the Rogers-Ramanujan identities. And if you let x be minus q, you get the second of the Rogers-Ramanujan identities. And that's it. Now, unfortunately, making this substitution in here is not something that's easy to do bijectively. And in order to do that bijectively, we had to have recourse to the Garcia-Milne involution principle. So we were able to construct a bijection along the lines of what Garcia and Milne had done, but it wasn't a bijective proof of the Rogers-Ramanujan identity. So we're still waiting on that, but we were hoping our bijection is a lot simpler than their bijection. So maybe someday somebody will succeed in taking our bijection. So it appeared as a short Rogers-Ramanujan bijection in discrete mathematics in '83, and then a much more detailed extension of this appeared in Advances in Mathematics toward the end of the decade. 1983, I received Doron's preprint of his proof of the Q Dyson conjecture. Actually, it is F Dyson, but the conjecture is known as the Q Dyson conjecture since it's the Q analog of Dyson's conjecture that George Andrews had made, that the constant term in that particular product, constant term with respect to the x's, is given by this Q multinomial coefficient. And Doron had put together an ingenious, a brilliant proof of this. The basic idea actually is due to Ira Gessel. And Doron was freely drawing on Gessel's idea. Gessel's proof of the Vandermonde determinant formula. It's probably not the shortest proof of the Vandermonde determinant formula. You could use symmetry to give a trivial proof. But I think it's the prettiest proof of the Vandermonde determinant formula. And that is simply to look at the left-hand product as a generating function for tournaments. So you've got n players, and each player plays each of the other players. Either player I wins or player J wins when I is against J. So the left-hand sum is really a sum over all possible tournaments. And the right-hand side is a sum over permutations. And the Gessel proof is simply to find a sign-reversing involution on the non-transitive tournaments. So if you've got a tournament in which player A beats player B, who beats player C, who in turn beats player A, that's a non-transitive tournament. And you can show that you can pair up the non-transitive tournaments with opposite signs so that they cancel out, and all that are left are the transitive tournaments. And the number of transitive tournaments is the number of permutations, and it's not hard to show that this is what you get. And so Doron had taken that idea and used it to prove Dyson's original conjecture. It was no longer a conjecture at this point. It had been proven by many people. And again, I think I.J. Good's proof of this result is one of the nicest. But the tournament approach is nice. In this particular case, you're no longer expanding that product. Well, the product is now the binomial xi minus xj is taken to the power ai plus aj. You're no longer expanding it. You're just looking for the constant term. And Freeman-Dyson had conjectured that that constant term up to a sign is the multinomial coefficient. And Doron was able to take Ira's idea and extend it.
And also Dominic Varda is equally important.
Ah, okay, yes.
No, Dixon, the special case, Zeilberger and Dixon's.
Okay,
so,
yes. So also drawing on Fuata's yes.
You don't really mean the constant term the way you've written.
You're right. I don't mean the constant term. I mean the appropriate coefficient of the monomial. Yeah. So the left-hand side generates multi-tournaments, and the right-hand side counts multi-words. And it's a nice bijection that clears out what you don't want there. So his idea for the Q-Dyson conjecture, which was an open problem at the time, was to extend this idea and look at it combinatorially. Look at the left-hand side as generating multi-tournaments, but now each tournament gets its own weight. So each tournament is weighted by a power of Q, and he was able to show that the tournaments that you don't want cancel each other out, that there's a sign reversing involution on those. And what he wound up with is that the tournaments that are left over are weighted by this particular statistic, the Z statistic. And the way the Z statistic is defined is you take all of the subwords in 2 letters. So if I've got a word in the letters 1 through N, where I've got A1 occurrences of 1 and A2 occurrences of 2 and so on, I just pull out the subword in the I's and J's and I look at the major index of that subword. So I'm simply taking that subword in I's and J's. I look at the positions where a J is immediately followed by an I, and I add up the position numbers of those particular J's. And I do that then for every pair ij, and that gives the Z statistic. As I worked through Doron's proof, I realized that he had the right idea, but he hadn't quite proven that that thing up there, the general multinomial coefficient, really is the generating function for the Z statistic. In other words, that the Z statistic is Mahonian. And fortunately, I was on leave that fall. I happened to be at the University of Minnesota. And so I had the time to dig into this and was able to prove that the Z statistic, in fact, is Mahonian. And we then wrote up the paper together. All of the real insights come from Doron, which is why his name is the first on that. I figured listing the authors as Zeilberger followed by Bressoud would send the message that this really was predominantly Doron's work.
No, you were very generous.
So it appeared in Discrete Math in 1985, and some other nice things came out of that. Ian Goulden realized that there were some directions in which it could be generalized, and I knew enough about the inner workings of what was going on there that I worked with Ian on this, and we did a paper for the transactions of the AMS, and also my only paper to appear in Communications in Mathematical Physics came out of this work. And I just want to mention that Ira Gessel and one of his students just a few years ago have come up with the first non-purely combinatorial proof. Well, in fact, the only other proof that's known of the Q-Dyson theorem that appeared in the proceedings of the AMS. The next piece of mathematics that I want to talk about is Kathy O'Hara's proof of the unimodality of the Gaussian polynomial. There have been many proofs of the unimodality of the Gaussian polynomial, but she looked at it combinatorially and come up with a rather complex combinatorial proof that would eventually get published in JCTA in 1990. But we really all owe a debt of gratitude to Doron for figuring out what was going on in Kathy's proof. And what he showed is that what you're actually doing is taking the Q binomial coefficient and breaking it down as a sum of polynomials, which, if you have an inductive step, you assume that this is going to be unimodal for all j's below this particular value. Then by induction, each of these summands is a polynomial with a unimodal polynomial with the same mode. So what this actually does is it takes a polynomial that's believed to be unimodal, and it actually breaks it down as a sum of polynomials with the same mode that are known to be unimodal. Well, that's an easy way of proving that you've got a unimodal polynomial, if it's a sum of polynomials that are unimodal with the same mode. And that turns out to be a very powerful result.